Right. Now, so today's the first topic for today will be the stellar deaths for the low mass star. Right. So we basically discuss what happened to a star when it is in the main sequence in the chart diagram, and then different processes it is going through, and how it exit from the main sequence go to this giant phase. And then again, after some reactions, we discussed that there is this horizontal branch that it goes through after this helium flash in the core region. And after that, let's see what happens. These low mass stars. So we are right around somewhere here in this diagram. Remember that I showed you this diagram before. So we are around this giant phase, discussing about this different phases of the star formation. Now today we will discuss about this white dwarf and planetary nebulas, how these are created, and if time permits, about the supernova explosions and the high mass stars as well. Right. Now, if you think about these main sequence stars in the HR diagram, so they will evolve off the main sequence and become giant stars. And this process is what we discussed yesterday. And what happens after that basically depends on the mass of the star. So which means uh, all the stars basically will go through a same kind of process inside their cores when they are in the main sequence, but when they enter into this giant phase and spend some time in the giant phase, then their fate will be decided by the mass of the star, right? Now, if we consider stars with the main sequence masses less than 8 solar mass, right? So if a star has a main sequence mass, that is the mass of the star when it is in the main sequence, because you will see that star will lose some of its mass during this process. Uh, so these stars actually they will never be able to burn carbon in their cores, right? The last week, remember that not last week, actually yesterday we discussed that first you have hydrogen in the core, and from the nuclear fusion hydrogen will become helium, and will be helium ash will be at the core, and after the required temperature is achieved, which is 100 million Kelvin, we discussed that the helium will become carbon in the core region through this triple alpha process, right? So that's what we discussed. Now, after this process, after you have carbon at the center, so what happens to the star will depend on its initial mass. Now, if the star has a main sequence mass less than 8 solar masses, these particular stars will never be able to burn carbon and make heavy metals, right? Remember, I told you that the process is this stellar evolution process is basically a competition between gravity and the pressure inside that. Now, the pressure creates basically from this nuclear fusion. Because of the gravitational collapse, the temperature increases in the core region, which will help to have this nuclear fusion. But to have a gravitational collapse, you have to have enough mass, right? Now, for these less mass stars, they will have carbon at the core, but after that, these stars will not have enough temperature at the central region to burn carbon into heavy material, right? And just to keep in mind that this M solar mass is refers to the mass of the sun, which is about 10 times 10 to the power 30 kilogram. Now these stars which are less than 8 solar masses, when they are in the main sequence, we refer those kind of stars as low mass stars. Right. Now, this when you have a main sequence mass greater than 8 solar masses, these kind of stars will refer as high mass stars. And for these high mass stars, they will gain enough temperature in the core so that they can burn carbon into heavy elements. Basically, this is because they have enough material to create this further gravitational collapse towards the central region and heat up to higher temperatures so that they can create this heavy metal, right? So that's the idea. But for these low mass stars, they don't have that condition. Right, so let's see first what happens to these low mass stars because they cannot produce heavy elements other than carbon. So let's see what happens to these low mass stars after they have carbon in the core, and we will consider the high mass stars separately because they will go through a different evolutionary process by creating more heavier metals, right? Now, when helium fusion ceases in the core of low mass stars, it leaves non-burning core of carbon ash. As I told you, you had helium at the central region of these low mass stars. When helium fuses, it makes this carbon ash, right? Instead of helium ash, now you have carbon ash at the central or core region of these low mass stars. Now, this carbon ash core actually it's non-burning, which means you will not get enough temperature to fuse it to heavy metals. So this the core will begin to collapse again once the carbon ash phase is done. You don't have a nuclear fusion at the central region again. So which means due to the gravity, the star will begin to collapse again, right? Because the heat, there is no heat generating at the central region to balance this gravity uh, coming from the outside or the coming from this gravity which collapse the star towards the central region. Now, but this collapse actually leads to increasing central temperatures. You know, when the outer material collapse towards the inner region, it will increase the central temperature, but this temperature will not enough to make heavy metals other than carbon. However, that increase of the central temperature will affect to this outside helium shell. So you know that we discussed there is a core right at the center and there is a shell outside. So there is a helium shell, so that will start burning, right? Once this temperature increases, right? And even in the outer region there will be a hydrogen shell which is still burning, right? You know that we discuss about these shells. You have a core which we mainly talk about, and after that you have this shell structure with different materials in these stars. Now what happens is, as in the previous stage, the outer envelope of the star will expand to compensate for this. Once you get this heating go to the outward direction, the whole star will start to expand. So it will increase the surface area. Now this phase we used to call as a supergiant. Right? Star is now called as a supergiant. So it will basically enter into from giant phase to the supergiant phase. And if you look at this thing from a diagram, this is in fact how it looks like when you have a star in the supergiant phase for a low mass star at the central region. So let me this central region you have a carbon oxygen core. As I told you, we mainly say that we have carbon, but there may be some oxygen as well because that both these processes can happen. And then you have a helium fusing shell outside, and then you have a hydrogen shell in the outer region, right? So that's you have around this central region, right? Now, then what happens is when the size of the star increases, uh, this will increase the luminosity of the star, because uh, your surface area increases, which means the luminosity should be increases, right? Now, because of that, the star will rise above towards the upper region in the HR diagram, nearly in a vertical. We call this as a vertical rise because this will go directly upward, roughly, and uh, this vertical upward direction rise is called as the asymptotic giant branch. Right? Asymptotic means increase like rapidly, and so these supergiants will continue to burn hydrogen and helium in the shell outside the core. Remember that you have a shell outside, hydrogen, and then you have helium. So while they are in the asymptotic, while they are in the supergiant state, they will still continue to burn hydrogen and helium, which are in these shells outside the core. In the core, you have carbon, and then you have this hydrogen shell, sorry, helium shell, and in the outer region, you have this hydrogen shell, right? They will continue to burn hydrogen and helium. Now, this the helium shell that you have just outside this carbon core, so this will become erratic and leading to helium shell clashes. Remember that previously we had helium core flash, right? So that's what we discussed now, and as the second step we will have this helium shell flash, right? Now once this happens, outer region of this star will continue to expand more and more and will become more unstable, right? Now, in this particular state, the star can experience a significant mass loss at this stage. So, the star will also lose some of its mass, right, because of this. And so, if I draw a chart diagram again, so this is how it looks like. Initially, the low mass star was in the main sequence, and then they will go out to this giant phase, and at the giant phase is where you have this helium flash. So that happens on the core. Sorry, you have the helium flash, and then you have something called after the helium flash, you will have the helium fusion at the core region, right? So this is what we discussed yesterday as the horizontal branch. And after this core helium fusion, it will go up again in the HR diagram to this asymptotic giant branch up to this particular point. Right? So that this is what we discussed up to now as a summary. Right? If you look at it, you can see that how HR diagrams are very useful when you remember and relate all this information, right? Once again, you have this initial point on the HR diagram as low mass star, and then after it burns up helium, hydrogen into helium, it will go up in this red giant branch. And remember that we talked about this helium flash. Once it happens, then the star will come down and go through this horizontal branch up to somewhere here, and then it will start this co-helium fusion, and with that it will go through this asymptotic giant branch because this outer uh, helium shell also actually start to have this helium flash, and with that it will go through this asymptotic giant branch, right? And at the end, the star will have something called planetary nebula, right? We will talk about that. Um, Now, after a few million years, the star's outer region is ejected into space. Now, remember that we discussed, I go back, uh, the star will increase in size and the increase in luminosity. So that's where you have this asymptotic giant branch, which is this phase right here. Now, after you have this asymptotic giant phase, increased luminosity, then what would happen is this outer region of the star will be ejected into space, right? Remember, after having this large surface area, the outer region is somewhat far away from this inner region. So it probably will gravitate less loosely bound gravitationally towards the central region, so that outer region will be ejected into space. Right? Now at this particular point, then the star will have two distinct components that you can identify clearly. That is, number one, you will have an expanding envelope, which is relatively cool and consists from thin gases. And this is somewhat looks like in spherical shape and will become transparent as well, right? And there are some envelopes actually that have very irregular shapes. Now, envelope means actually, you know what envelope means, right? This is that this outer region of the star, which will go out as a separate unit to the space. And then you have a very small dense core that is mostly made from carbon ash, right? From the star's core. From the star's core, helium burning continues for a while in the core's outer region, but eventually dies out. Now, just understand again what happens here. If I go back to this particular phase, for the low mass stars, you have non-burning core, which consists of mostly from the carbon ash. And apart from that, this helium shell is actually burning. Now, when helium shell, which is in the outer, is the next layer, when it start to burn, uh, this outer envelope of the star will expand to compensate for that. And this stage is what we call it as a supergiant, right? And as you see here, you have the carbon oxygen core and this helium fusing shell and also a hydrogen fusing shell. Now what happens is again, uh, this increasing size will lead to this particular process called asymptotic giant branch, which means with the increasing size, you increase the surface temperature and hence the luminosity. So the star will go through this asymptotic giant branch phase and will become a star that is more luminous and more giant. So this is what you see here. After you have the helium right here, you have the helium fusion, and after that you have carbon ash. At the same time, this hydrogen with the hydrogen shell, so the helium shell burning in the outer region, the star will get expanded and will go into this, go through this region. And once you go up right here, you will have two components in the star, that is this expanding envelope in the outer region, and then you have very small dense core which is mainly consists from carbon ash, right? So make sure that you understand these two clearly. And this carbon ash core will remain as it is, but this expanding envelope will be ejected out to the space, right? And these odd looking objects is what we called as planetary nebulas, right? So this is something, some objects that looks very beautiful through a telescope if you used to have a chance to get observed these things. But remember that this name called planetary nebula. However, there is no relation between planets and these nebulas, right? So this is these planetary nebulas are created as a result of this stellar evolution process for low mass stars, right? Basically, this is basically because when the star get expanded, you will get a carbon core at the central region, and then there will be an outer envelope that will expand to the outward region, which we called as the planetary nebula, right? So remember that there is no relation between a planetary nebula and planets, right? So there are no relations. It is just the name that came through in these ancient times for different reasons, and the name stayed as it is. Once you have a name, it's hard to change it again. So these are actually some of the images of planetary nebulas. They seems to looks beautiful when you look it through telescopes and have these pictures. And this one called NGC 6826, and this is around 2,200 light years away, and located close to the constellation Cygnus. Right? And this is called IC418, also called as the Spirograph Nebula. So you can see that they have different names, and this is one of the popular ones, the Cat's Eye Nebula, or NGC 6543, and this is around 3,200 light years away from Earth. You can see that these are like objects that are so far away from us. Like once again, you can see the chart diagram just to give you an idea about what we are discussing here. And you can see there is a star called Sirius B right here, right? So in a minute, you will see that this is a white dwarf star, which is
Okay, so I guess I would assume that. Can you hear me now?
Now we can hear, sir.
Yes, sir.
Can one of you please confirm whether you can hear me now? It seems now it is working.
Yes, sir. We can.
Yes, sir.
Hello.
Yes, sir, we can hear you.
So I'm assuming that. Uh, can you hear me now? Okay, right. So let me start again. So what I probably repeat what I have done. I'm not sure how long that was. It wasn't like hearing. Thank you for that. And for some reason, the mic has gone out. Let me just have it. So I have been talking about these white dwarf stars. So what I discussed is actually once you have this stage with the star that you have a central core, carbon core, and you have the planetary nebula. And after some time, with the age, what happens is this planetary nebula will disperse and disappear from the view, and what you will have is this dense carbon core as the remaining object, and this is what we called as the white dwarf star, right? And these stars are normally very dense objects, and they are very smaller. And if you compare it with the sun, it will be 100 times smaller compared to the sun. Now, still you have one force here, right? That is gravitational force. Regardless of whether you have a small mass of or the large mass, gravitational force will continue to collapse this star towards the central region, right? Now, to make a balance for this star, there should be some force that should coming out towards the outward region to hold this gravitational collapse, right? Since you don't have any nuclear reactions going inside that, this the pressure that you need from the internal region to stop this gravitational collapse is provided by something called electron degenerate pressure. Now, this happens when you have this gravitational collapse. All these electrons will be tightly packed in the central region, and you know that electrons repel each other. That particular feature in the electrons will provide an additional pressure inside this star, right, at the central region. And this particular pressure due to the compact of electrons is called as the electron degenerate pressure. So this is the pressure that will create a force which will help to balance this gravitational collapse at the end, right? Because you don't have any nuclear fusions now going on these stars to balance the gravity. So for a white dwarf star, it is the electron degenerate pressure that will balance this gravitational collapse, right? So that's how these white dwarfs are remaining as balanced stars at the end, right? So as white dwarfs also ages, they gradually cool off and fade, and they will produce a white dwarf sequence in the HR diagram. So that will be the ultimate finishing point. And here is the track of the white dwarf in the main sequence in the HR diagram. As you see here, that if you look at uh, our star, our sun-like star, because sun will become a white dwarf one day because it's a low mass star. The diagram here shows the changes in the luminosity and the surface temperature for a star with the mass like the sun. as it's near the end of its life. Right? I am just reading the caption here, which will give you a lot of details. And after the star becomes a giant star, which is this, so let me show this to you. Giant star, which is this particular point right here, it will lose more and more mass as this core begins to collapse, right? So it will start losing its mass, and this mass loss will expose the hot inner core. So once you lost the mass and once you have gone to this planetary nebula region, this will expose this hot inner core, which will appear at the center of the planetary nebula. Right? In this stage, the star moves across the diagram to the left as it becomes hotter and hotter during its collapse. So what will happen is when this the central region keeps collapsing, the star's temperature will become increased, hotter and hotter. Like so, it will go through this path because of that. And at the same time, you know that its temperature will increase, but and go to this point up to the point B. Uh, and at first, the luminosity remains nearly constant, but as the star begins to cool off, it becomes less and less brighter. So after some time, the star will begin to cool off, and the brightness will go down. So which means the white dwarf, this particular white dwarf star, will go down and come to a point somewhere here in the lower left-hand corner. Right? So the star begins to cool off and becomes less and less bright. So which means it will be around this point C at the end, right? Then we call that as a white dwarf, and also will continue to cool slowly for billions of years until all of its remaining store of energy is radiated away, right? So what happens is when there is no force acting in the central region, the remaining energy will be radiated out, right? Now, according to this model, we can think that what will happen to our sun. So we assume that our sun will lose around 46 to 50% of its mass during these giant stages based on the models that we have. Right now, sun is one solar mass. It will be around half a solar mass when it go through this phase and become a white dwarf. Right. So this is what will happen to our sun. But you don't have to worry about that now because it will take another 4.5 billion of around 5 billion years to for the sun to exit this main sequence phase and start uh, these next phases, which goes to A, B, and C points. Right? And here is an example of a white dwarf. So white dwarfs are actually not stars that you can see easily because you can see in the chart diagram they are right down in the lower left hand corner, which means their temperature is somewhat higher, but their luminosity is not that much because of this the smaller size. Right? Now in the left hand image, now you see here, this is actually the Sirius star system. Now one of these stars you can see from your naked eye when you go outside. Right? In the image number A in the left hand side is taken by the Hubble Space Telescope. If you look at it carefully, you should be able to see two stars. So there is one large star right here, which we called as Sirius A. And if you look carefully, there is another star right here, very small faint star, which is what we called as Sirius B, right? Now you can see that even from the Hubble telescope, the Sirius B is barely visible, which means you you will not be able to see this particular star, but you will see the large Sirius star, right? But if you look at the same image through an X-ray telescope, this is how it looks like, right? In the right hand side, now you can see the star in the lower left hand side has become brighter, right? Now the Sirius A, which is the one that it looks brighter in the optical region, is now looks fainter, And from the in the X-ray image, Sirius B, which was the faintest star in this image, has become brighter. Now you should be understand why this happened, because for a white dwarf, now these are things that you can actually, for a white dwarf right here, you can see that their surface temperature is higher. Because of that, they should emit more X-rays, right? So X-rays are like high energy, so they should emit more X-rays. So that's why when you take an X-ray image, you can see the Sirius B star clearly, right? So this is just an example why astronomers use these different regions of the electromagnetic spectrum with different telescopes, right, to look at these stars. Right, here is an example of this is M4. M4 is a globular cluster, which we discussed yesterday. You know what's a globular cluster is now, right? Remember that we talked about two types of star clusters. One is called a globular cluster and the other one is called open cluster. And this is a globular cluster. And if you enlarge this small region in this globular cluster and have this image on the right hand side, you can see number of white dwarf stars. So I guess there are around 75 or something like that, as far as I remember. All these white circles that you see in this image in the right hand side are actually white dwarf stars. The bright yellow stars are actually giant stars. They are not white dwarf, but you can see a lot of white dwarfs right here. And here is an enlarged version. By the way, I just need to mention like a very uh, small thing here, though it's practical. Now sometimes the students used to ask from me, this is a very basic thing if you know photography, but why you have these trails like two lines like this and like that for this particular star? Is it a feature of that particular star, or is it something else? This is actually, anybody knows the answer, by the way? Why do you see these trails? You probably have seen it in the other, it's not here. And you can see in this image also, there are these, in these bright images, you have these lines like that. Is that a feature of these stars, or is it something else? Right, so actually this is actually not a feature of a star. What has happened here is the camera got overexposed to these bright stars. So what happens is when you have an image which is overexposed, these are CCD chips. So each pixel has a capacity that it can bear in terms of the light photons. When that capacity goes out, uh, so they will transfer, or so those light photons will be distributed to other nearby photons. So we used to tell that these are like streaks type of things. So what has happened is that this light got overexposed for these bright stars, so that you will see these the trails, which we call as these trails kind of thing, or streaks, which are actually not useful if you are doing actual research. We have to remove all these stars because they are overexposed and they are scientifically actually not valid, right? But actually they are in most of these pictures in the internet, because they makes this star looks beautiful, but scientifically it's completely wrong. So we actually not even use those stars, right? So they are basically overexposed. So that's what has happened. Now let me, so that's the end of this death of low mass stars. Now let me go to this. Before I go into the high mass stars, remember that I told you there is a small section I want to go through that will help you to complete this tutorial, right? So that's about these Kepler's laws, and probably Newton's gravitational laws. These are very basic things, but still it is nice to know about that. So because of that, let me just take this half an hour to explain briefly about these laws so that you can get an idea to complete the tutorial that I have posted on the first few sections. Right, so, and by the way, in the next day, which is most probably will be on next Thursday, which is a holiday. Again, I will try to get time in the morning. If possible, I will let you know tomorrow evening about that. And that will be actually about, so we will discuss about death of high mass stars, right? Today we will discuss what happened to these low mass stars. Just keep this in mind as a story, which will make it easier for you, right? With all the details. But for now, let me just switch a little bit uh, to look at what happens for these, just to look at these planetary laws that we should know in astronomy. So that will be, let's see, yes. So let me. So this is actually based on a chapter that I have in this book that I asked you to look at. So I will directly take information from there and we talk using this presentation. Let me share this with you. Right, so I would assume that you should be able to see my shared screen, which is about orbits and gravity, chapter 3 of the book. So I have mentioned the chapter number as well. If anybody is interested to read through, this is actually a very nice book for introductory astronomy course. If you need to read through, you can get a lot of information. I'm not going to go through each and every information, but I have also have these figure numbers here. If anybody needs to go and look at the book, so they will be kind of aligned with the figure numbers as well. Uh, Now, this is International Space Station, which is one of the uh, objects that you can we have in our orbits, which is actually not what I will not talk about the details about the International Space Station. By the way, that there is an app called Spot the Station or something like that that you can just download and track where the International Space Station is, the location of that. And for every 90 minutes, this will complete one circle around the Earth. So which means there are times depending on its orbit that sometimes this particular spacecraft or the International Space Station will go above our sky so that you go outside and look at it. This is visible for your naked eye, by the way, not as you see in this picture with all the solar panels and everything, right? Because this is so far away, you will not see all the details, but you will see just a dot that is cruising uh, above the sky. So that's something extra. So what I actually want to discuss is these three laws about the Kepler's. So Kepler has found three laws which is directly related to this planetary motion. And of that, um, the first law is actually that he has found all the planets that we have in the solar system is basically going around the sun in elliptical orbit. So that is his first observation. He actually did his observations based on the data from another astronomer called Tycho Brahe. So if you don't know this history, the Kepler used this Tycho Brahe's data which he had gathered, and then he did some calculations and figured out that the first thing actually that he has figured out the orbit of the Mars. So that is that why I have mentioned here. So what he has done was he first realized that the mass is going around the sun in an elliptical orbit, and For example, the semi-major axis, now when you have an ellipse, so there are certain things that you have to remember. Ellipse has two axes. This axis from here to here, we call that as a major axis. And I will upload this presentation to you so you can go through some of the details, which I am not going to discuss each and everything. And half of that distance is called as the semi-major axis length, right? And so this will be important for us. And for an ellipse, we have something called eccentricity. Now to make, you will understand this better if you think about a circle. Circle has the same radius for each direction. Or it has um, one radius, so that's why you call it as a circle, right? So its eccentricity is basically zero because it is not eccentric, right? It is a symmetrical. You have a symmetrical shape for a circle. Now for the ellipses, you have this eccentricity, and how elliptic an orbit is depend on the eccentricity value. Now, uh, so Kepler has found that all these planets going around in elliptical orbits, and the eccentricity of the orbit of Mars is only about 0.1. You can see that these eccentricity values are very small, right, compared to the circular orbits. There is an eccentricity on each of these orbits for planets, but the value is very small. Now, this may be not what you see in these pictures when you see in the internet, right? So they looks like very eccentrical or very elliptic orbits. But in the actual case, these eccentricity values are very small for the planets. So that's why it's hard even to find this eccentricity like 300 or 400 years ago. So that's the Kepler's first law. And the second law is he deduced that or discovers that planets sweep out equal areas at equal times. Now the idea is, so his first law stated that all the planets are going around elliptical orbits like this, and uh, all these ellipses, they actually have two focus, or we call this as forking as a plural word. So there is one focus here and there is one focus here. Now the planet is around this elliptical orbit and sun is on one of these focuses, right? So in the other focus you don't have anything. So that's what you see here. Sun is on one of these foci, and then you have a planet going around an elliptical orbit. What happens is in general, using the general knowledge, you can think that when planet is very close to the sun, which means around this area, it should go faster, right? Because of the force is higher. And when it is further away, it will slow down, right? Now this leads to this particular law, which we called as law of equal areas, or Kepler's second law. So what he stated here is, in equal times, it will sweep out equal areas, which means for a particular time t, a planet may go from point 1 to point 2 in this side, but the distance that it will cover in the other side will be smaller at the same time. So which makes this particular area shaded from yellow color and named as A will be equal to this shaded area in the right hand side named as B, right? So that's because it will go faster when it's close to the sun and it will be slower when it is further away from the sun. Right? So that's the idea. And the Kepler's third law is probably the most important for us. So what he has stated here is the orbital period of a planet, if you denote it from P, and if the length of the semi-major axis of this elliptical orbit denoted from simple A, P squared is proportional to A to the power Q. Right? So that is what he has stated, and this is still valid. Right? So Kepler's third law says that the planet's orbital period squared is proportional to the semi-major axis of its orbit cubed. Right? So that's what he has stated. So make sure that you remember this law. You have to remember it. So there is a very special thing about this law. If you use correct units, it's very easy to do calculations here, right? As an example, if if T is calculated in terms of years, T is the orbital period, uh, the distance or the distance from sun to a particular planet or the length of the semi-major axis is calculated in terms of astronomical unit, you can remove that proportional sign, and instead of that you can make these two equal to each other directly, right? And this is a very important finding, and I expect that you can use this and solve problems, right? This is a very simple calculation, and this Kepler's third law is applying for all the objects that are orbiting around the sun, including Earth. Now, here are two examples that I have. Uh, Actually, I was expecting that you could be able to complete this. Can you try complete uh, at least the first problem? Just look at this law right here and try to find the answer for the first one, and I will discuss the second one, right? So I will give you probably 2 minutes for this one. This is just a substitution, just to give you an idea how this law works. The question is, imagine an object is traveling around the sun. What would be the orbital period of the object if its orbit has a semi-major axis of 50 astronomical units, right? So you are given uh, the length of the semi-major axis, you need to find the orbital period. Just have a try, and if you have a calculator, you probably will be able to answer the question as well. Um, so I will give you probably 1 or 2 minutes. If you have an answer, just post it here. Once again, the uh, law is right here. P squared equal a to the power 3. So all you need to do is use that and try to have an answer, right? So just do it yourself, because these things is what you will have to do in your exams as well. So make sure that you understand and know how to use Kepler's third law. I post an answer, so I will be back in within 1 or 2 minutes to look at your answers, right? And after that, we will discuss. Right, so I just had one answer, which is equal to 353.55 years. Thank you for that. And uh, Right. So the answer actually would be, so just had one answer. So make sure that I don't have actually time to give you more time here, but make sure that you do it yourself and try to understand how to use these laws, right? So these are very simple, but still I have the experience that students get lost in the exams because of the units that you have to use, right? So they sometimes think that, okay, this is very easy, we will do it in the exam, but you have to get familiar with the units, especially in the astronomy, otherwise you will be in trouble, right? So you have to, now if you, for example, plug the values in terms of light years, this equation will not work in this way. Then you have to do a lot of conversions and those type of things, right? Make sure that you use the correct form of the equation with correct units here. Uh, that is important, right? Here are the answers. So your answer is basically correct. So this is close to 353 years. You just need to plug the values here because you are given the length of the semi-major axis in terms of astronomical unit, right? That is the advantage here. And the second question is very similar to that. Again, you are given the semi-major axis. Now, make sure that you check whether you are given the length of semi-major axis or the major axis, right? So what A means is the length of the semi-major axis, right? And if you are given, let's say, the length of the major axis is 50 astronomical units, then you have to take the half of that for A, right? So that is important. So make sure that you understand that particular feature there, right? And here are two other examples that I have put here with the solution just to show you how it works. And these are already available in the book as well. So I just directly copied it from the book. But if you need, you can require the book as well. But it's here as well. Just see how the units work out here, right? So that is important. Right, so here I have summarized all three Kepler's laws. The first one is each planet moves around the sun in an orbit is an ellipse with the sun at the center. Uh, is there anyone who wants to talk or have something to ask? I just have some noise from one of your, maybe one of your mics. So feel free to ask if you have any questions to ask. Right, so let's continue. And the Kepler's second law is, as I stated, that the straight line joining a planet and the sun sweeps out equal areas in space in equal intervals of time. And then the third law, if I state in words, that is the planet's orbital period is directly proportional to the cube of the semi-major. The square of the planet's orbital period is directly proportional to the cube of the semi-major axis of its orbit, right? So that is the third law. And as an honor for the Kepler, this is some piece of information that if you are interested, you can go and look at it. This new spacecraft, which is launched, I guess around 2009 or something like that, which we call as the Kepler mission, is it's named under Kepler to honor him because the primary purpose of this Kepler mission is to look at these extra solar planets, or I mean exoplanets, right? So that's something, some extra information. And just probably to remind you about the Newton's laws, I assume that you already know about this. I'm not going to explain it, but I will have it in this presentation. Newton has basically three laws that you know, and you know that these ejecting a rocket to the space basically works under Newton's third law, right? So you probably should understand it. And here are some like basic things. And this law, uh, this concept about the conservation of angular momentum is also important when you are talking when you do astronomy. because there are a lot of places that you use it. And I am not explaining it because have I assume that you probably have learned this stuff in your physics courses, even in your A levels. And this is how you write the Newton's law of gravitation, which is g m1 m2 over r squared. And this is also you already know, right? So what I mainly need to talk about those actually these Kepler's planetary laws, but then the Kepler's planetary laws actually have modified, and and this picture actually this is made for a different course, so that I have put some extra information about how this how you why you feel this weightlessness in the space, right? So you can just read through those. So what I want is to come up to this particular point. Newton's version of the Kepler's third law. Now, the Kepler's third law that we have taught is actually describe the orbit of the objects whose motion are described by Newton's laws of motion, right? Basically, the Newton's formulation of these and the new, hello, hello, is that you can't hear anything? Is it true? It seems like my microphone is actually working. Okay, so let me just finish this last section, and you can probably get this recorded version if you can't hear it, right? So it seems like the microphone is working, so you should be able to hear me clearly at this point. And if not, you will get the recorded version of the lecture. Right, so basically the Newton's formulation introduced that this additional factor of masses of the sun and the planet both into this Kepler's equation, and these both these expressed in terms of the units of the sun's mass, right? Now the Newton's version of the Kepler's law therefore written as a cube is equal to m1 plus m2 times p squared, right? So that's how you used to write the Newton's version of the Kepler's law, right? Now, actually what has happened to the Kepler was, remember that we had this equation, right? Which directly relates p squared and a, and he just has number one here in front of the equal sign. The reason is actually when you consider a planet, and the sun, for our solar system, the mass of a planet is very small compared to the mass of the sun. And because of that, this value of m1 plus m2 can be approximately equal to one solar mass. And because of that, uh, the Kepler's law initially was actually an approximation, which is relatively correct, and we are still using it, right? So it is just that if you have two masses that are comparably like close to each other, this is where you need to use this Newton's version, and especially for two other like objects, specifically for for a planet like Earth, and for the mass you can still use the older version of the Kepler's law, because when you compare the two masses, the mass of the sun is very large, so that your final answer will not affect that much, right? And there are some information about the ellipses that you can just go through, and how the motions of satellites and spacecrafts happen. So what I actually want from here is just to have you an idea about this Kepler's laws, Newton's laws, and Newton's modified version of the Kepler's laws. Right. So these laws will be helpful for you to complete the some of the questions in the tutorial which I have posted. Right. So let me. Yes. So this is all I would like to discuss about this section. I will post this presentation by reducing some of this stuff so that it will be easier for you to look at exactly what you want to look at. And anybody have any questions up to here? You can ask.